Hello, and welcome to the Trending Tech Show. I'm Alex, and today we're diving into one of the most influential developments in the world of AI, transformer architecture. Joining me is Mike, a machine learning expert whose research focuses on natural language processing and deep learning. Mike, great to have you on the show.
Thanks, Alex. I'm really excited to talk about transformers. There's just so much happening in this space, and their impact on AI has been nothing short of revolutionary.
Let's start at the beginning. For our listeners who might have heard about transformers but aren't sure what they are, could you explain what a transformer architecture is and why it matters in the context of AI?
A transformer is a type of neural network architecture that processes sequential data, like sentences in language or even images split into patches, but in a fundamentally new way compared to previous models like RNNs or LSTMs. Transformers rely heavily on a mechanism called self-attention, which lets the model weigh the importance of every part of the input sequence when processing each element. This makes transformers much better at capturing context and relationships over long distances, which is essential for understanding language, generating coherent text, translating between languages, and much more. Their design also allows them to process entire sequences in parallel, making them much more efficient to train on modern hardware.
You mentioned self-attention as a key component. Can you break down, in really simple terms, how the self-attention mechanism works? Maybe with an analogy.
So imagine you're reading a book and trying to understand a sentence like, "The cat sat on the mat because it was tired." To figure out what "it" refers to, your brain looks back at the whole sentence and realizes it means the cat. Self-attention does something similar but mathematically. Each word in the sequence transforms into three different representations called query, key, and value. The word we're focusing on, say it, checks how much it should pay attention to every other word by comparing its query to the keys of the other words, producing attention scores. These scores are then used to build a weighted representation that helps understand the context just like you do when reading.
That's a great analogy. So, when you say query, key, and value, are those just different ways of representing a word for this process? And why bother with all three?
Exactly. They're just different mathematical projections of the word's meaning. Using all three allows the transformer to decide not just how important other words are, but also what information to actually use. The query asks, "What am I looking for?" The key answers, "What do I offer?" And the value provides the actual content to be considered. This setup allows the model to dynamically adjust which words it focuses on depending on the sentence and the task at hand.
I see. And I've heard the term multi-head attention tossed around a lot. How is that different from self-attention? Or is it part of the same process?
Multi-head attention is actually an extension of self-attention. Instead of doing this attention calculation just once, the transformer does it multiple times in parallel, each with its own set of parameters. These are called heads. Each head might focus on different aspects of the relationships in the data. One could learn to pick up on grammar, another could specialize in finding which noun a pronoun refers to, and so on. At the end, all these perspectives are combined, giving the model a rich, nuanced view of the data.
That's fascinating. But one question comes up. If transformers don't process data sequentially, like RNNs, how do they know the order of words, which can be crucial in language?
Great question. Transformers do lack an inherent sense of sequence since they process everything in parallel. To fix this, they use something called positional encoding. Let's say we have a sentence. Each word not only gets its usual embedding, but also an extra bit of information that tells the model where it sits in the sequence. This positional info can be generated mathematically, often using sine and cosine functions, or sometimes it's learned by the model. It's like labeling each word's location, so the model knows the order, even though it's looking at everything at once.
How does this architecture compare to older approaches, like RNNs and LSTMs? Why was the shift to transformers so important?
Before transformers, models like RNNs and LSTMs processed sequences one step at a time. While they could handle language tasks decently, they struggled with really long-range dependencies, meaning they'd forget things said earlier in a long sentence or paragraph. They also couldn't easily be parallelized, slowing down training on large datasets. The self-attention mechanism in transformers can directly connect any two spots in a sequence, no matter how far apart, and can do so all at once, making them much more efficient and effective, especially as our data keeps getting larger.
When people say that transformers revolutionized NLP, what are some of the reasons for that? What can we do now in language processing that was hard or impossible before?
Transformers truly changed the game for NLP. First, they enabled a major leap in state-of-the-art performance for tasks like translation, summarization, and question answering. Models like BERT, which uses only the encoder part of the transformer, and GPT, which is decoder only, achieved breakthrough accuracy. Another huge leap is in transfer learning. Historically, you needed to build a new model for each task. With transformers, you pre-train on a massive amount of text, say all of Wikipedia, then fine-tune the same model for your specific job. This made powerful NLP tools accessible to everyone, not just big research labs. They also paved the way for few-shot or zero-shot learning, where a model can handle a new task with just a small amount of guidance, or sometimes none at all.
Can you give us some practical examples of what these models are powering today in the real world?
Absolutely. For starters, text generation tools like ChatGPT rely on transformer models to generate coherent and relevant answers, summaries, and even stories. Translation services, like those from Google, use transformer-based architectures to convert text between languages, often in real time. Transformers are also behind systems for summarization, like BART and T5, question answering, like BERT and Roberta, and even recommendation engines. But it goes beyond language. Vision transformers now match or surpass classical convolutional neural networks for classifying images, and there are multimodal models like CLIP and DALL-E that can connect images and text in creative ways, generating pictures from descriptions or matching captions to images.
It sounds almost limitless, but are there any notable limitations or challenges that transformers face?
Yes, definitely. One big limitation is self-attention's computational cost. It scales quadratically with the sequence length. That means if you double the length of your input, the work doesn't just double, it quadruples. This becomes a bottleneck for really long sequences, like entire books or genetic sequences. Researchers are working on ways around this, such as sparse attention methods, like in longformer or reformer, or splitting data into chunks. There are also challenges around interpretability. The models are so complex that it's sometimes difficult to understand why they made a particular decision. And since training these models requires a huge amount of data and computing power, there are concerns about accessibility, cost, and environmental impact. Not to mention, they can pick up societal biases from their training data.
That's an important point about ethical and environmental considerations. Could you elaborate a bit more on what the risks are, especially in terms of bias and sustainability?
Of course, with transformers, the sheer amount of data and compute needed for training large models can lead to a significant carbon footprint. This raises questions about sustainability, especially as models keep getting larger. In terms of ethics, since these models are trained on massive internet datasets, they can inadvertently learn and propagate biases, like stereotypes or discriminatory associations that exist in their training data. Given their black box nature, it's also hard to spot these issues or trace specific errors. Addressing these risks is a major area of research. There are also concerns about accessibility, since only organizations with access to large amounts of computing power can train or even use the biggest models.
You mentioned that models like BERT and GPT use different parts of the transformer structure. Can you explain a bit about the encoder-decoder setup and how modern variants adapt the original transformer architecture?
The original transformer architecture is split into two main components, the encoder and the decoder. The encoder processes the input, like a sentence, creating a rich representation. The decoder then uses this encoded info, along with its own self-attention, to generate output step by step, like translating to another language. Modern models specialize this setup. BERT, for example, uses just the encoder. It reads the whole sentence at once to understand context for tasks like classification or question answering. GPT, on the other hand, uses only the decoder for generating text, predicting one word at a time based on previous context. Some models, like T5, use both in a text-to-text framework. The key is that the architecture is very flexible and can be adapted to task-specific needs.
Transformers have also moved beyond just language, right? What are some examples of how this architecture is being used in other domains?
That's right. Transformers first became famous for text, but they're now used in computer vision, where vision transformers split images into patches and treat each as a token, much like words in a sentence. These models have rivaled and sometimes surpassed classical convolutional networks for image tasks. In multimodal AI, models like Clip connect images and text, enabling powerful search and creative tools. In science, transformers are helping with protein structure prediction, like in AlphaFold, drug discovery, and speech recognition models like Whisper. The pattern is, if your problem involves sequences, whether it's words, images, audio, or even molecules, transformers can often help.
There's clearly a lot of excitement and ongoing innovation. What are some of the main areas researchers are focusing on to address transformers' challenges, and what might the future look like for this architecture?
Some key directions include improving efficiency, so models can handle longer inputs without chewing through so much compute and memory. Approaches like sparse attention, model distillation, making smaller, faster versions, and quantization, reducing precision to save space, are all active areas of research. Interpretability is another. It's important that we understand why models make the choices they do, especially in high-stakes applications. Reducing biases and making models more transparent and energy efficient are ongoing efforts too. Looking forward, we'll likely see more generalist models that can juggle text, images, and actions together, a move toward true AI generalization. Also, as tools become more accessible, we'll see even small teams leveraging these advances, not just big tech companies.
This has been an incredibly helpful and enlightening overview. To summarize, transformer architecture has changed the field by introducing self-attention for contextual understanding, multi-head attention for richer insights, and parallel processing for turbocharged efficiency. It's now at the heart of everything from translation and chatbots to image analysis and scientific discovery, but there are still hurdles around efficiency, accessibility, and ethics. Thanks again for joining us and sharing your expertise.
Thanks, Alex. It was a pleasure. Always great to spread the word about the incredible things happening in AI.
And thank you to our listeners as well. If you enjoyed today's episode, don't forget to subscribe to the Trending Tech Show for more deep dives into breakthrough technologies. Until next time, I'm Alex. Stay curious.